awesome AP Chemers. We're going to talk about equilibrium in gaseous systems. So lots of reactions involve gases, and we have been talking about equilibrium in terms of molarity. So today we're going to talk about the equilibrium constant in terms of pressure. So we've spent a whole chapter on gases, and we looked at how pressure is related to the number of moles of that gas. And we looked at reactions where we can link from one substance to another using moles, of course. But we also linked from one substance to another using partial pressures if they were gases. So just like we can express equilibrium constant in terms of concentrations, we can express it in terms of pressures or partial pressures. So to write the equilibrium expression in terms of pressure, we write it as Kp, so capital K for the equilibrium constant, but with a subscript P to indicate that it's in terms of pressure. And you do it the same exact way, except instead of using brackets for concentration, you use P for pressure. And we are only going to include gaseous substances, of course, here, because they're only ones that contribute to pressure. So for this one, it's products over reactants as always. So Kp is going to be the partial pressure of the Cl2. And you don't put that because it's a liquid. You don't put that because it's a solid. So that's it for this one. For the next reaction, you're going to say Kp is the partial pressure of the H2O and to the fifth power. Remember, it's products over reactants raised to the power of their coefficients. So we don't include that because it's a solid, and that is a solid as well. Let's look at the next one. So Kp is the partial pressure of the SO3, and that's squared, over the partial pressure of the O2, and that is cubed. We do not include the solid sulfur in there. So the same exact way as regular K, except we put P instead of brackets, meaning that it's the partial pressures. Now when we calculate these, we need to use ATMs for the units of pressure. So we can't use PSI or millimeters of mercury or kilopascals or any of that stuff. It has to be in atmospheres. Now there is a relationship between Kc and Kp because we can relate moles over volume, which is basically molarity, and pressure, right, from PV equals nRT. We can derive this equation, but you don't really need to use it anymore. And so we're not going to spend the time to derive it, but this is how you relate Kp to Kc. So Kp is equal to Kc times RT. R, of course, is the ideal gas constant. T is the temperature in kelvins. And then delta N is the difference in number of moles of gas. You do products minus reactants. So let's write that down. Delta N is moles of gas in products minus moles of gas in reactants. So again, you do not need to use these equations or convert between Kc and Kp. We used to have to do that, but they took that out of the AP exam. So this is just for your notes to know. The one thing you need to know about Kp relating to Kc is when are they equal? So when is Kp equal to Kc? Well, if you look at the equation, Kp would equal to Kc if this whole thing was 1. And so when would this whole thing would be 1? That's when delta N is 0, meaning that the moles of gas in the reactants are equal to the moles of gas in the products. That's when Kp is equal to Kc. So that's the only thing that you need to know when you relate them. So when delta N equals 0, which means moles, number of moles of gas in products equals the number of moles of gas in the reactants. Okay, so you'll only be able to, or be asked to convert between them if delta N is 0, which means they're equal to each other. So let's try some problems here. Let's look at this one. It says ammonium hydrogen sulfide decomposes. So that's ammonium hydrogen sulfide right here. It's a solid, and it decomposes into two gases, ammonia and hydrogen sulfide. So let's look at part A here. It says solid ammonium hydrogen sulfide is placed in a flask at 25 Celsius. At equilibrium, the total pressure inside of the vessel is 0.659 atm. Some solid remains at the bottom, which makes sense because if you have equilibrium, you're always going to have some reactants left over and some products, of course, formed. We want to calculate Kp. So let's think about what we know here. Well, we're given the reaction, of course. We're also given the total pressure. So we know that P total is given to us as 0.659. We know that P total is going to be equal to the sum of the partial pressures of all the gaseous species there, products and reactants. So in this case, these two are gases. This is not a gas, so it does not contribute to the pressure. So it is equal to the partial pressure of the NH3 plus the partial pressure of the H2S. If your reactant was a gas, then you'd add it as well. So we know that the total pressure is 0.659 atm. Well, what else do we know? Can we relate the partial pressure of the NH3 to the partial pressure of the H2S? You can, because they're both products. So if they're both products, you can relate them based on the molar ratio, right? For every NH3 that you form, you're going to form an H2S. You cannot relate reactants to products in terms of moles or pressures total, because not all of this reacts, right? We're at equilibrium. So, but you can relate a product to a product. So if we say that the partial pressure of NH3 is X, then the partial pressure of the H2S is also X. Sorry, that should be a plus there. So 2X is equal to 0.659. So X, which is the partial pressure of the NH3, which is also the partial pressure of the H2S, is going to be half of that, which is 0.330 atm. We want to calculate Kp, so we're going to write the Kp expression. It's going to be the partial pressure of the NH3 times the partial pressure of the H2S. Now that we have them, we can plug them in. So 0.330 atm times 0.330 atm. You multiply them together to get your Kp. You get 0.109. The units would be atm squared in this case, but remember, they don't care about the units for K, whether it's Kp or Kc, so you don't need to include it in there. Okay, let's look at B. So it says more NH3 is injected. So we've reached equilibrium, but then we added some more ammonia. Okay, so more of the product. So it took some time, but then equilibrium was reestablished. The partial pressure of ammonia is now twice the partial pressure of the hydrogen sulfide. We want to find the new partial pressures of the two products. So let's think about what we know. Well, they're telling us that when we've reached equilibrium again, the partial pressure of the ammonia is twice the partial pressure of the H2S. So if H2S was X, then ammonia would be 2X. Well, what else do we know? What would be the same? What would remain the same? Would the total pressure be the same? No, because we added more ammonia, right? What would be the same? Well, the only thing that would be the same is Kp, as long as we didn't change the temperature. Remember, for any reaction, the equilibrium constant is constant as long as the temperature remains the same. The only thing that would change it is if you change the temperature. So the equilibrium constant, whether it's Kp or Kc, should remain the same if you're at the same temperature. So if we write our Kp expression, we know that this is still going to be equal to 0.109, right? And now we know that the partial pressure of the ammonia is twice that of the H2S. So now we can solve for X. So this is 2X squared. And so X, which is the partial pressure of the H2S, is equal to 0.233 atm. You need units here. because it's the partial pressure. And then 2x, which is the partial pressure of the NH3, would be 2 times that, so 0.466 atm. And so those are our answers. Let's look at part C. It says NH3 and H2S are introduced in a 1 liter flask. So this looks like a totally different reaction, right? Like, I mean, the same reaction, but we've started a new vessel, right? We're not continuing with these numbers here. So we still have the same type of reaction, NH4HS, solid decomposing to form NH3 and H2S. But we have totally different numbers now. So it's telling us NH3 and H2S are introduced into a 1 liter flask at 25 Celsius. The initial partial pressure of each gas is 0.500 atm. We want to calculate the moles of NH4HS formed when the system reaches equilibrium. So it looks like we actually don't have any of this. We are just introducing these here into a reaction vessel. So initially it says that this is 0.500 atm. This is 0.500 atm. This is a solid, so it doesn't really contribute to the pressure or anything like that in an ice chart. So let's do an ice chart. Okay, so we're starting out with these two, and as time goes by, we are going to have a reaction between the two of them, and we're going to use up some of them to form some of this solid, right? So the change would be that some of this gets used up. We don't know how much. We're going to say minus x. And it's a 1-to-1 ratio here, so this is also minus x. And so at equilibrium, this is 0.5 minus x, and this is 0.5 minus x. Well, what do we know, again, that is the same between this part and parts A and B? Well, the only thing that's going to be the same, since this is the same reaction, is Kp, the equilibrium constant. I mean, the equilibrium constant will always be the same as long as you have the same temperature. This is 25 Celsius, and in here it was also 25 Celsius. So we know that Kp is still the same 0.109. So I'm going to write the Kp expression here. It is the partial pressure of the NH3 times the partial pressure of the H2S. And I know that this is still 0.109. So what I can do is I can plug these not concentrations, but partial pressures. So this is 0.5 minus x times 0.5 minus x, and I can solve for x. So x, when you calculate this, is equal to 0.170 atm. What does x mean? Well, x was the change, right? This is how much of the ammonia or how much of the H2S was used up in order to form NH4HS. Let's write that down. So this is the pressure used up. And let's pick one of them. Let's pick ammonia. Pressure of NH3 used up in the reaction to form the NH4HS. So now what? Well, what we could do is figure out how many moles it took for this pressure. So if this is the pressure that is used up, then how many moles were used up? We can do a PV equals nRT for ammonia or for H2S. It's going to be the same way, same thing. So I could do a PV equals nRT, plug this in. This is the pressure that's used up, so I can figure out how many moles of ammonia were used up and then go from moles of ammonia to moles of my solid. So I'm going to do a PV equals nRT, and I'm going to do it for ammonia. You could do it for H2S if you'd like. It's going to be the same thing. So 0.170 atm. My volume is 1 liter. N is what I'm solving for, and remember this is for ammonia. R is 0.0821 atm times liters per mole Kelvin. and my temperature is 298 Kelvin. So I punch this into my calculator. I get 0.00695 moles of ammonia. That's how much reacted or got used up. So I can use my molar ratio now. If I know how much of the ammonia was used up, I can figure out how much of the solid was formed. This is just stoic. Moles of ammonia, moles of NH4HS. It's 1 to 1. So you get 0.00695 moles NH4HS formed. That was a good problem. Let's do one more. Nitric acid, which is HNO3, often has a brown gas, NO2, over the liquid. A NO2 molecule can bind to another NO2 molecule to form a dimer. Dimer, like how polymer is many parts. Dimer, di means two, so 2 parts. So you take an NO2 and an NO2 together and you form a dimer. NO2 and its dimer, N2O4, so when you put 2 together you form N2O4, are in equilibrium, where N2O4 gas is in equilibrium with 2 NO2. So for every one of these, that decomposes to form 2 NO2s. 2 NO2s combine together to form that dimer. And they give us Kp. They tell us if the total pressure of the equilibrium mixture is 1.5 atm, what is the partial pressure of each gas? So our reaction is N2O4 yields 2 NO2s. Well, what do we know? We're given Kp and we're given the total pressure. So let's see, P total is going to be the partial pressure of all the gases in the reaction. So we have N2O4 and we have the partial pressure of the NO2, right? Both together. Now, can I say that the partial pressure of the NO2 is twice as much as the N2O4? The answer is no. I cannot say that. I cannot relate it. Now, earlier, in an earlier problem, we were able to relate these right here. Those were both products, and we said the partial pressure of this one is equal to the partial pressure of that one. Why could we do that? Well, because they're both products, and they're both coming from the same source. And so using the molar ratio, I can say, well, for every one of these that forms, one of these forms, right? But I cannot relate a reactant to a product if you have a reversible reaction. Why not? Because for every one of these that gets used up, yes, I form 2 of these, but I don't know that all of this gets used up. Maybe only 10% of it gets used up. Maybe 50% of it gets used up. So if I know the partial pressure of this, I do not know that the partial pressure of this is twice as much, because I don't know how much of this is actually going to decompose to form this. That's the whole point of the equilibrium constant, is to tell us, well, at equilibrium, what is the ratio of products to reactants? So I don't know how these relate. All I know that together they equal to 1.5 atm. So what I could say is, if the partial pressure of the NO2, let's say, was X, then the partial pressure of the N2O4 would be 1.5 minus X. That's all I know. I know that together they add up to 1.5. So if this was X, this would be 1.5 minus whatever that X is, or vice versa. So what I can do now is I can write the Kp expression and plug X in for this and 1.5 minus X in for this, and solve for what X is. So Kp here is going to be the partial pressure of the NO2 squared over the partial pressure of the N2O4. So my Kp is 0.11. So that is equal to, we said the NO2 is going to be X, so X squared over 1.5 minus X. And I can solve for what X is. And X is going to be, I chose that to be my partial pressure of the NO2. You solve for X, you get 0.4. I believe it's 0.40 atm. And then 1.5 minus X is the partial pressure of the N2O4. So 1.5 minus that is 1.1 atm. And those are my answers.